Okay, so a reminder that a polynomial has positive integers. So like, look, the example here, this just real quick, that's your example. Notice how your polynomial, guys, is the sum of power functions with positive integers. Okay, so the fundamental theorem of algebra says that if the degree of the polynomial is at least 1, then there will be at least 1 0 in the set of complex numbers. Now, that seems like common sense, right? Don't you think? But that's what the fundamental theorem of algebra says, that if it's a polynomial and the degree is at least 1, then there will be at least 1 0. Ta-da. Okay. So we're also going to talk about the leading coefficient test. Do we know what the leading coefficient has, what effect it has on the graph? What effect does the leading coefficient have on the graph of the polynomial? What does it tell us? Yes, it definitely does that. It stretches it. But what does it tell us as far as the end behavior, though? The direction. So like if as x approaches infinity, f of x approaches infinity, in other words, if the polynomial goes up and to the right forever, then my leading coefficient is positive. And if my polynomial goes down and to the right and down forever, then my leading coefficient is negative. Okay, we know that. All right. So let's talk about, excuse me, the real zeros of a polynomial. Okay, this right here, this statement, if a minus b is a solution, a minus bi, excuse me, is a solution of p of x, then a plus bi must also be a solution. In other words, complex zeros, or any zeros at all, complex, just as a reminder, complex includes real and imaginary numbers. So complex zeros always come in conjugate pairs. So that is called the conjugate root theorem. That's what that's called. Conjugate root theorem. And it says that if a plus bi is a 0 of a polynomial, then a minus bi will also be a 0. Okay? All right. We also want to talk about repeated zeros. So let's go to our calculator, and I have this function in my calculator right here. It's in Y2. Everybody see this? I have Y1 turned off. So if I have Y2 and I see this, okay, I'm going to zoom in. I'm going to zoom in a little bit, I think, so we can see better what I want to talk about. I zoom in here, and I need to go to the left to like -5. Okay. All right. So what I see is there are 2 zeros. Now, by looking at the function, I can tell that the zeros are 1, -3, and -4. And I want you to notice that the x minus 3 factor is raised to the first power. It's raised to an odd power. Also notice that x plus 4, the x plus 4 factor is raised to the third power, an odd power. So, and now let's look at the graph. 1 is a 0, and -4, excuse me, is a 0. Both of those were raised to an odd power. They both go through the x-axis. But x plus 3, the x plus 3 factor is raised to the second power, an even power, right? So notice how that is affected on the graph. The 0 is -3, isn't it? If I said x plus 3 equal to 0, don't I get -3? Well, when I look on the graph at -3, does the graph go through the x-axis or does it just touch it? It just touches it. So that's what we need to remember about repeated zeros. So these are called repeated factors or repeated zeros, where if the factor repeats here and here, if the exponent is even, it's going to touch the x-axis. It's not going to cross. And if the exponent is odd, it's going to go through the x-axis. Got it? Okay, any questions so far? All right. So now we're going to talk about, yesterday we reviewed how to do synthetic division and what the remainder theorem and the factor theorem says. So I'm not going to talk much about that today. We're going to get a lot of practice with synthetic division in just a bit. Okay, so everybody good? All right, what does the rational root theorem say? Let's go all the way over here. This is what the rational root theorem says. it says that if my polynomial has integer coefficients, then every rational zero of f has the following form. The numerator will be a factor of the constant term, and the denominator will be a factor of the leading coefficient. Now, let's make sure we all understand what the difference between a rational number and an irrational number is. A rational number is a number that can be written as a fraction. So like 1/3 is rational, 2/5 is rational, 157 is rational, 0.3 repeating is rational because that's a third, isn't it? 0.6 repeating is rational because that's 2/3. Now, a non-terminating, non-repeating decimal is considered to be irrational. Think about the number pi. Think about the number e. Non-terminating, non-repeating decimals. Got it? Okay. So this is not talking about irrational numbers. This is talking about rational numbers. Every rational zero of a polynomial will be in this form. The numerator will be a factor of the constant term. The denominator will be a factor of the leading coefficient. Okay. So we'll talk more about that in just a bit. Okay. All right. So now I want to get into the meat and the bones of this lesson, which is, okay, so if we want to start talking about what's called the region of interest. And we also want to talk about Descartes' rule of signs. Does anybody remember learning about Descartes' rule of signs last year? You know that emoji? Okay, great. And then we're also going to talk about upper and lower bounds, and we're going to review how to find zeros. Okay, does everyone have their graphing calculator in front of them? You need your graphing calculator for sure. So we're going to use this example, this number 1. Do you see how I have I've snipped it, so make it to give myself more room. Okay, so for each one, we're going to find several things. We're going to first find the region of interest. Now, the region of interest is a circle. The region of interest for a polynomial, so let me give you just a little sketch. So polynomials do like this, right? Polynomials do like that. Well, so the end behaviors are not very interesting, according to this theorem. The end behaviors are not very interesting as x approaches infinity or as x approaches negative infinity. But in between the two end behaviors is where all the stuff, the exciting stuff happens. Like, in other words, the turning points and the zeros. That's where all the exciting stuff happens. So look, a region of interest is a circle, okay? So the way that we find the region of interest is, let's look and see what the rule says. Let's use our highlighter. The normalized equation is found by dividing each coefficient by the leading coefficient. Divide each coefficient by the leading coefficient, and then take the value of the coefficient that has the greatest absolute value and add 1. And this circle of radius r is the region of interest. So this is very simple. You just have to know what to do. So to get my region of interest, which is, like I said, that circle of some certain radius where all the exciting stuff is happening. That's what we're looking for. So you're going to divide each one of your coefficients by the leading coefficient. What is the leading coefficient here? 1, right. So if I divide each one of these leading coefficients by 1 and then take the absolute value of the largest one, what do I get? 58. That's right. And then add 1 to that, and what do we get? 59. So my region of interest is a circle of radius 59. Okay. Okay, that's the first thing I want you to be able to do. Okay, the next thing is we're going to talk about Descartes' rule of signs. Descartes' rule of signs is a way for us to find how many possible positive real roots or how many possible negative real roots. Notice I said real. Not imaginary. We know there are polynomials that have imaginary zeros, right? But we're not talking about those. We're talking about the real ones. So according to Descartes' rule of signs, this is what you do. You're going to take, for the function, you're going to take P of X. There's P of X right here. And count the number of sign changes in the coefficients. How many times does the coefficient change sign? Do y'all agree? Carter says twice. What do y'all think? 1 and then 2. Oh, 3. Uh-oh. So from positive to negative, and then it stays negative, and then it changes from negative to positive, and then positive back to negative. So how many sign changes? 3 sign changes. So 3 sign changes. 3 sign changes for P of X means 3 positive real roots. Do I need to review that a root is the same thing as a 0, is the same thing as an x-intercept? All the same? Got that? Okay, so I could say 0 or root, it's the same thing. 3 positive real roots. Now, or, this is the rule, or less than that by an even number. What's an even number? 2, 4, 6, right? So 3 possible positive real roots, or less than that by an even number. So what's 3 minus 2? So, or 1 positive real root. And what happens if I subtract 2 again? What is 1 minus 2? It's negative, so we're done. So according to Descartes' rule of signs, since there are 3 sign changes for P of X, that means there are either 3 positive real roots or 1. Okay, then we need to find P of negative X. So in order to find the number of possible negative real roots, we're going to find P of negative X. So P of negative X would be, every time we see an X, we're going to plug in negative X. And then we're going to simplify. Okay, so everybody see what I did? Plug in, every time you see an X, plug in negative X. And now we're going to simplify. So negative to the 4th power will be positive, won't it? And then negative X to the 3rd power will be negative, and a negative times negative 4 ends up being positive, doesn't it? Stay with me. And a negative X squared is positive, so that stays minus 15X squared. And that becomes negative 58X, and that's minus 40. Okay, so now we found P of negative X, and we're going to count the number of sign changes again. How many sign changes? How many sign changes do y'all see? I just see 1. Does everybody see 1? Okay, so what that means is 1 sign change for P of negative X means 1 negative real root, or less than that by an even number. I keep saying that, or less than that by an even number. So let's suppose you counted 4 sign changes. It would either be 4 or 2 or 0. Let's say you counted 3 sign changes. It would be 3 or 1 or that's it. You see what I mean? I only found 1 sign change, so it's just 1. Okay, do y'all see how that works? Okay, so Descartes' rule of signs tells me how many positive or negative real roots by counting the sign changes for P of X for positive real roots, and then for P of negative X, counting the number of sign changes. Does anybody have a question? Now we have to find the zeros. Okay, so in order to find the zeros, 3, we're finding zeros. In order to find zeros, we're going to use our calculator. So let's go to our calculator. Let's go to our calculator, and I'm going to turn this one on and turn this one off. Okay, and this is what I've got. Let's see, zoom 6. Okay, all right, does that look good? Do I see all of what's going on, do you think? My region of interest? Do we expect it to be going up in both directions? Is it x to the 4th? Yes, we expect that. Okay, so let's find. So what you're going to do first is you're going to find the zeros, as many as you can, using your calculator. We're going to make that simple, okay? We're going to show our work with the synthetic division, but we're going to first find as many rational zeros using our calculator. Now, I think I can see just by looking at it that it's -4, 1, 2, and 5. Do y'all think? Okay, so what we're going to do, let's start with -4. How are we going to use that? Well, so I'm going to say the zeros are -4. What are they? 1, 2, and 5? Is that what they were? Okay, so if the zeros are -4, then I should be able to do some synthetic division, right? And factor the polynomial as much as I can. That's what I want you to do. So I'm going to list my coefficients. 1, -4, -15. Not doing it with me right now is going to be a detriment, I promise. Except for Zach. He's got an excuse. He's debilitated right now. Okay, so we're going to do our synthetic division. And let's see what we get. I'm hoping I get, what's that? What's -15 plus 32? 17? Yeah, I don't know what 17 times, I think that's -68. Is that real good? Oh, look at that. Did I expect to get 0 as a remainder? Yes, because the remainder theorem says that, no, the factor theorem says that if you get 0 as a remainder, then x plus 4 is a factor, right? And if x plus 4 is a factor, then that means -4 is a 0. Okay, and what else do we know? We know that 1 is a 0, so look what I'm going to do. I'm going to divide by x minus 1. Notice I'm using my calculator as an aid, so I don't have so much work to do. Y'all notice that? Oh, look at that. So what I have so far is I have p of x equals, I want to factor it as much as I can, x plus 4 times x minus 1, and then I get x squared minus 7x plus 10, which I know that I can factor again. Now, this is the deal. If you can't factor it again, then you would need the quadratic formula, wouldn't you? If you couldn't factor it again, in other words, if the other two zeros were irrational or even imaginary, then you would need to use the quadratic formula to find them, okay? All right, but we didn't have to in this case because they were all rational. Okay, and then the very last thing is I want to talk about upper and lower bounds. Okay, so let's say, okay, we've got this polynomial. Let's draw a sketch. We had -4, -4 is a 0, 1 is a 0, 2 is a 0, and 5 is a 0. So it does some, whoa, I didn't even go through. Let's see, it goes something like this, does something like this, something like that, right? Okay, so I have my region of interest, and so what I want to do, an upper bound is, and I'm just going to show you how to do it because I think that's going to make it easier on everybody. Pick whatever the largest 0 is. What's the largest 0 in this case? 5, right. So let's pick 6. So we're going to start with one more than the largest 0. And you're going to divide by x minus 6. Pick one more than the largest 0, and you're going to divide by x minus that, okay? And I want you to notice, let's see what we get here. So I'm just going to do my synthetic division, and I'm going to go fast because there we go. Okay, now look at the coefficients of the quotient. What I'm looking for an upper bound is I want the coefficients for an upper bound. The coefficients need to be all positive. Are they all positive? No, they're not. So I'm going to pick the next higher number. So let's pick 7 now. So we're going to do 7. We're going to do synthetic division for x minus 7. Don't worry, I'm going to explain what all this means in just a second. You know that I will. And I'm going fast just for time's sake. 100. Oh, look at that. Okay, so I'm not going to do the last one because I know the last one gives me my remainder. I want you to notice the coefficients of the quotient are all positive. Okay, so what that tells me is that my upper bound is 7. Okay, so 7 is my upper bound. Now, what is an upper bound? What it tells me is is that since all the coefficients are positive when I do the division, it tells me that 7 is too big. What it's telling me is that all of my zeros are less than 7. That's what it's telling me. Now, this was a process that was used a lot before graphing calculators were invented. So we're using our graphing calculator to help us, but we're learning all the algebra and the advanced math, okay? Okay, so 7 is my upper bound because all my coefficients were positive. Okay, so now I'm going to look for a lower bound. So I'm going to go, what was my lowest zero that I found? -4. So the lowest zero I found was -4. So let's go one less than that. Let's go to -5. Let's do synthetic division and divide by x plus 5. And what I'm looking for is, I'm going fast, sorry. Now, -50 minus 58 would be -92. Is that right? Okay, so stop there. We can stop there. And notice all coefficients are all alternating signs. That's what we're looking for. Notice that the coefficients of the quotient are alternating signs. Alternating signs means lower bound. Now, what does that mean? Lower bound means that since it's a lower bound, all of the zeros are bigger than that, okay? So when you're finding your upper and your lower bound, just remember that. You're finding like a range that's going to narrow down your choices for zeros, even though we have our graphing calculator, though we're just learning the process, okay? So we would say that our upper-lower bound is between, what's the upper bound? 7. What's the lower bound? -5. So in between -5 and 7, there's my upper bound. Okay. Are there any questions about that?